I'd like to give you an overview of 3 Excel files that I've made available out on Jay's Toolbox that represent thermodynamic properties for 3 different refrigerant substances. In other words, R134A that you use frequently, R22 that is used, I think, a little less frequently, and then, gosh, we'll see what it is, but I believe it's also ammonia used nowadays for very large scale refrigeration systems. So let's go ahead and get started and see how you can access these thermodynamic property tables in Excel. Yes, my memory was correct. And so I'm going to show you the 3 different Excel files of refrigerant tables tools for R134A, R22, and ammonia. I'm going to try to show you how to download those files from Jay's Toolbox. Give you a little test drive. How can these files work for you right out of the box? And then a quick reminder on what you need to understand in terms of what is the phase of a substance and what is the state of a substance. And that's really necessary for you to be able to access about any of these phase change type substances thermodynamic tables. Okay, and so here's a screenshot. I'll try to go live to show you. Once you go to Jay's Toolbox at jaystoolbox.vt.domains, you'll drop down the Toolbox menu, go to Excel Docs menu, and then you'll be able to drop down the category Excel Refrigeration, and that's where you'll find the 3 Excel files that I'm going to try to show you about. And this is what they'll look like. It's you see very repetitive R134A refrigerant, R22 refrigerant, and ammonia refrigerant. And what I've done is in the PDF format, I have copied and pasted the numerical values from the textbook right into Excel. And very similar to the video that I created about H2O steam, water, steam tables tool, you'll see that it's the same organization. 3 basic types of tables in 6 worksheets. The tried and true temperature table in English and SI, the tried and true pressure table for saturation properties in English and SI, and then finally superheated vapor properties in English and SI. So those are the raw data table worksheets. And then I've got 4 worksheets, 2 in English and 2 in SI, regarding a lookup tool that I've created for myself and you for looking up saturation properties using a linear interpolation scheme, and then also superheated vapor properties using a double interpolation scheme, both in English and SI. And as a reminder, I'm hoping that you've worked through in a serial manner on these videos. In my work in Excel, when I have a yellow cell, that's the key to myself and to you, the user. Yellow cell is a manual numerical entry. Anything that's a white cell is a formula. Don't modify those or you risk really getting yourself in trouble. And so, of course, once you look at these, you'll see that there are multiple worksheets. I call them tabs, and that's the way they're divided. And recognize that there are interlinks between the tabs. So, for example, the lookup tabs, the tabs that use interpolation schemes, are always going back and looking at either the temperature table or the superheated table. Now, the lookup schemes do not involve the pressure table data. That's just the way I've created the interpolation schemes. So do recognize there are inter-tab links in the formulas for interpolation. And so I just want to say that at a previous video I created, I think we'll go into more detail in the steam tables tool, because that's how I got started in this. So I created, because most of my work involved steam, less proportion of work involved refrigeration, but the light bulb went on for me that, wait a minute, if I can create these interpolation schemes for steam tables, all I need to do is replace the raw data with refrigeration properties, because they're all those thermodynamic tables are arranged in the same manner in terms of the properties that are tabulated. So it really became a fairly easy job to pull out all the steam table properties and replace those properties numerically with R134A, R22, and ammonia properties. And the mathematics really was exactly the same. So that's my key to go live. Well, I'm going to try to see the overall file organization, a little demonstration of how would you use the standalone features, and then talk about how would you solve problems using these thermodynamic property tables in Excel. All right, so that is that's my cue, and see if I can figure out how. Okay, I'm out of PowerPoint. I'm going to minimize that. Let me show you how to access these files first before I give you the demo. Here we are at J's Toolbox. We'll look at the Toolbox menu and drop down to Excel Documents. Okay, and let me scroll down a little further. Excel Documents, and then here is Excel Refrigeration. So I'm going to click on this link. Click, there we are. And here's our new page. And so we're going to scroll down. This is for refrigeration type Excel files. And there's a demo file, but here's what you would download. If your problem is R134A, you would download this Excel file. And then scroll down a little further. And here is ammonia refrigerant tables. And then finally, R22 refrigerant tables. So you've got your choice of 3, or you could look at the others as well. Okay, so let's say you've downloaded those. So I'm going to go to Excel, and since I've already downloaded, I possess all those files on my PC. I'm going to open up the R134 Excel file, and it's going to be representative of all 3 of those substances. So here's the organization. Notice here. So look at all these tabs down low. Okay. So I have multiple tabs. And so recognize on my intro worksheet, these are hyperlinks that will jump you to the various tables and applications, instead of you having to go to the bottom of the file and click on a particular tab. If you have, say, an SI problem and you're interested in the temperature table for saturation, vapor dome, just click on SI, and that jumps you immediately to the temperature table SI tab. I'm going to scroll up, and here, this is just a tried and true copy and paste values out of the temperature table for R134A. Look how familiar it is. So you see how, look, it looks nearly identical to what you see in your textbook, okay, with increasing temperature table, because the leftmost column is the saturation temperature. That would be like boiling point at a specific pressure. Second column is pressure of the temperature table. We go back to intro. Let's look at SI units for pressure table. Okay, and here's our pressure table. It's a shorter amount of rows, okay? Various pressures in the left column with saturation temperature in the second column. And so do recognize that the pressure table and the temperature table, these are numerically identical. The only difference is columns 1 and 2 are flipped, okay? And that's simply a courtesy for engineers. If you have pressure, it becomes easier to look up values in the pressure table. However, if you're doing interpolation schemes, you can just stick with the temperature table. And the good argument for that is that there are more rows to deal with in the temperature table, which means you've got more interpolation precision if you stick with the temperature table for your vapor dome. Okay, back to intro. Now, okay, so that is superheated vapor properties. Let's look at SI units for superheated vapor properties. Remember, of course, in your textbook, there are a bunch of different pressures tabulated for superheated vapor. So there's a bunch of subtables. And what I've done here in Excel is I've stacked those tables one next to one by one, going down the rows, and it makes it easy to exactly see what you're doing. And this is tailored for the interpolation scheme when you're given a pressure and a temperature. So having these stacked in this manner enables the double interpolation in Excel. All right, back to intro. Now let's look at the tools. So right out of the box capability tools here. Let's say you have an SI problem and you've got some strange number. Let's say you know that for R134A, you have a temperature of, let's say, minus 5.5 degrees C. That's cold, okay, right? No, it's a refrigerant, okay? Well, what we do is I go in and minus 5.5. Let's go to our temperature table and see where would minus 5.5 be. I'm going to click on temperature table SI down here, okay? Minus 5.5. Well, here's minus 8, and here's minus 4. So minus 5 and change is somewhere in between here. Okay, let me go back to the tool. Okay. It's going to be property lookups SI. My temperature is 5.5. So what I do in the interpolation scheme is I find the best match rows in the temperature table that straddles minus 5.5. And so I found those rows and I write down the properties VF, VG, UF, UG, and on, HF, HG at both of those rows. And then I do a straight interpolation between the temperatures at those rows compared to minus 5.5. And so let's click on one of these numerical results here. Okay, notice here, I just clicked on H sub F. So G5. This is, so if you look at this formula, you see that it's not totally Greek. You see that if you use your imagination, it's a lot like a straight linear interpolation. It's some number, cell AB5, plus it's a proportion. Look at this proportion. Here's the numerator divided by the denominator, it's proportion, times the maximum span, which is cell AC5 minus cell AB5. So that's the idea, and it's repetition of linear interpolation for all these properties. And so this could be a time saver for you. I want to encourage you, though, that you have to be able to do this by hand first, and you have to be pretty good at it because you're going to be taking your quizzes and your tests, and you're not going to have this handy Excel tool to do the linear interpolation for you. So step one, get good at linear interpolation on your own first, using the temperature table, using pencil and paper. Once you feel like you're good at it, this tool may really help you in your problem solving, homework problem solving. So you get the idea. Put in any temperature, yellow cell, 12.62. Okay, you enter that in, and so 12.62. If I go to the temperature table, 12.62. Well, Excel goes out and it finds these two rows that straddle 12.62, and it writes down the various saturation properties, F and G, and does the linear interpolation for whatever that was, 12.6. Let's go back, 12.62. All right. So that's this tool. This is out of the box. You can do this over and over again without any modifications, okay? Let's say you have the pressure and you're interested in saturation properties under the dome. You enter the pressure, okay? And let's say it's 425. Okay, so you've entered 425. and you want the other properties, all the other vapor dome saturation properties at 425 kPa. Let's go to the temperature table, 425. So we're looking for a pressure of 425. Well, look at here are the two rows that straddle 425. So again, straight interpolation. So this time we're searching in this column for 425. Simple matter of writing down the various saturation F and G properties and then doing the linear interpolation to get the result at the in-between number. Property lookup SI, there we are, 425. So this gives you an idea how to quickly get your properties under the dome. Now, a little more, let's go back to intro. A little more complicated for getting properties for superheated vapor because now you've got to enter two independent properties. Let's click on SI Superheated Tool. So in this, I have several blocks, but let's look at this big block. Double interpolation if you know pressure and temperature for your R134A. So this is a big interpolation block within Excel. Okay, let's see how does it work. Well, the user, you or me, we put in the pressure in kPa and the temperature in degrees C. Now, this is the bottom line result. These blue cells are the bottom line result. And you see that they're very simple formulas. See me clicking on these cells. They're very simple formulas because they're transferred from the big bottom line interpolation down below. Here's the way this works. So pressure 157. Well, Excel, I've created the formulas for Excel to go out and find the straddling pressures. What pressures straddle 157? Well, the answer is that in the superheated tables, the entries for 140 kPa and 180 kPa straddle 157. We have to create two tables, two subtables for those pressures because we've got to look up a temperature of 23 degrees C. And so let's see, 23 degrees C, my subtable. I don't see 23, but look, here's the row, two rows straddle 23. And over here, here's two rows that straddle 23. So I have to do the second interpolation between these two to get my second temperature interpolation. And so I go through and I do all that work and I check my work to verify I'm doing it right. And so this big block is what enables you to do or Excel to do the double interpolation with pressure and temperature known. And so you can go right into this and you can enter the pressure and temperature and immediately get back all these properties for superheated vapor. Now, let's scroll down on this worksheet a little bit because there are situations in engineering where, especially if you're studying an isentropic process, it is very common for us to know the pressure and entropy pair instead of pressure and temperature. So I've created another double interpolation scheme where you put in the pressure. Again, it finds the two straddling pressures that straddle the number that your input number, 193, but entropy. But now we're interpolating in this column, 1.1. And so here's the two rows for 180 kPa associated with trying to find an entropy value of 1.1. And let's see. And here are the two rows at 200 kPa looking at that straddle entropy 1.1. So I hope you get the idea. And so this big block enables you to find the properties of superheated vapor when you know the pressure and the entropy. Okay, and then finally, I've got another block because it's also common that you may know the pressure and enthalpy of a superheated vapor. And this last block in the superheat lookup, in this case SI table, you enter the pressure and the enthalpy, and the double interpolation is done for you again, and you get this result. But I do want to stress that doing this in Excel, it is sort of step 2 for you. I really want you to work hard on learning how to do this by hand, learning how to do the interpolation, both for the vapor dome, that's easy, single interpolation, superheated vapor, double interpolation, much, much harder. You must learn how to do this by hand before coming right to Excel to get these property evaluations. But once you're pretty good, once you're satisfied you can do it pretty well by hand, this can be a big time saver for you, and it can become a problem-solving tool for you, so you can start solving refrigeration problems in Excel if you wish. Okay, I hope that, and so that's a pretty quick overview of the way all 3 of these refrigeration table tools work. Okay, so let's see if I can. So this block right here, this is your raw data. These are simply data tables, no mathematics in these tabs. These tabs here, yes, mathematics, which is linear interpolation for the saturation properties. In other words, properties along the vapor dome, H sub G, H sub F, V sub G, V sub F, saturation pressure and temperature. Those are pretty easy. But then the lookup tool for superheated vapor, much more complex because it's double interpolation. And I expect those problems for you at the undergraduate level are only a few. So, so not to worry, not to panic. Okay, I think that covers what I wanted to cover for you in these refrigeration tables. So let's go back to PowerPoint. Do want to point out, so recognize that the pressure table in English and SI, I've included those worksheets as a courtesy to you, so you can have those tables in Excel accessible to you with whatever, however numerically you have in mind what you might want to do. But the lookup tools, the saturation lookup tools, do not use the pressure tables. It only uses the temperature tables, whether you know pressure or you know temperature. I'm going to run through this section much more quickly than I did with the steam. It is my hope that the steam tables intro, this is a rehash of what I covered in the steam tables entry, but I need to put it in here to remind you of what you really need to understand, no matter what the substance is. You have to understand what is the phase of a substance and what defines the state of a substance. Tried and true vapor dome that's representative of any substance. Recognize you've got, when you're to the right of the vapor dome, superheated vapor, okay? Under the vapor dome, well, that's going to be a saturated mixture, a mixture of saturated vapor, saturated liquid. Easiest to understand is when you're laying on this left side of the vapor dome. That would be a liquid that's right at the boiling point. Okay, so depending on the pressure, there's a boiling point associated with each pressure. So it's a liquid right at the boiling point. If you continue to add heat, you boil, so you're transforming some of that liquid into vapor. And as you continue to add more and more heat, you get more and more vapor until finally you get to the point where everything becomes a saturated vapor. You could no longer see that substance. It would become a saturated vapor. So that's what's laying on the right-hand side of the vapor dome. To the left of the vapor dome is a compressed liquid. For refrigerants, it's a little unusual. Typically, refrigerants in regular operation do not get subcooled very far below the boiling point, the saturation temperature. And so we don't worry too much about compressed liquids for refrigerants. Typically, we're dealing with the coldest things get would be saturated liquid for refrigerants. But let me go back. So the important thing for you to recognize is to be able to identify or understand the different phases of a phase change substance, particularly refrigerants. Very cold when you're down in the saturation, lower pressures, very low temperatures here. In the superheated vapor region, you can get pretty high temperatures. At higher pressures, higher temperatures, the temperatures for refrigerants even can go pretty high. This critical point here is for H2O. Okay, so what's a state? And the important takeaway here is that two independent intensive properties fully defines the state. Two independent intensive properties defines the state. So in the superheated vapor phase, it's a pick list. Any two of these properties defines the state. If you're a saturated vapor, if you're on the right-hand side of the vapor dome, any one of these properties defines the state, plus X equals 1.0, the quality, the mass of the vapor divided by the total mass. Well, in this case, superheated vapor, that's 1.0. It's all superheated vapor. So any one of these plus X, the property X equals 1.0, that defines the state as a saturated vapor. What defines the state for a saturated liquid is any one of these plus X equals 0. 0% vapor divided by total mass. Okay, that's the quality, the property quality, 0.0 defines the state. And then finally, under the dome, saturated mixture, any one of these plus some number X, the quality between 0 and 1, fully defines that state in the saturated mixture phase. Finally, in the compressed liquid phase, well, H2O and other liquids, even refrigerants, are considered incompressible in the compressed liquid phase, and those properties depend only on the temperature of the substance. So even for refrigerant, you were going to go to the temperature table, and as long as you know the temperature of the compressed liquid, you look up V sub F, H sub F, U sub F, and S sub F to get the properties. And that pretty much covers it for using the Excel refrigerant tables tool. So there's 3 of them for 3 different refrigerants. It's important that you have a good feel for what's a state of a substance, what defines the state, 2 independent properties, and what is the phase. Is it superheated vapor? Is it a saturated mixture? Is it saturated vapor or saturated liquid, or is it a compressed liquid? That's the phase. And then recognize the importance of units. And that's why in these tools, I've got multiple worksheets using different units that I do my best to spell out. It's not just a bunch of numbers. It is column headings with the property and the unit tied to it. Okay, so I hope that helps. I blazed through these because it's my hope that you went in and have looked at the steam tables intro to get a more thorough or more detailed feel for the way these thermodynamic tools in Excel work. All right, don't hesitate to reach out if you're trying to work with these and need a little more direction. I'll be happy to work with you if you need a little more direction.